So it's Sunday, and been working on software stuff mainly, and I encountered a few problems. Just want to give an update on the software and some measurements that I took. The first thing I was interested in was when I'm trying to think of a way to do this auto tuning, I need to know how to adjust. And so I did a little experiment where I adjusted the DAC control word by 100 counts, and I saw how the error increased. And so basically, here's 0. I was getting, either 1 or 0 errors every cycle. And then I made it, the DAC control word 100 more. And so I was getting, 1 error. And with 200, I was getting 1 or 2. 300, I was getting 3. 400, I was getting 3 or 4. And so what I basically surmised was that 100 DAC counts basically equals 1 error a second. So if I initially power this on, or once I wait till it's stable, if I'm getting 5 errors a second, then I probably need in the software to reduce it by 500. So that was interesting. And then I noticed that my count was sometimes not working properly on the system. I would get 128 as the error, and I was stumped. And I looked and looked and looked. I had no idea what it was, but I discovered a couple things. One of them is if you look at the display. I was actually I ran this for a very long time, and the elapsed seconds overflowed, and that's contained in an integer, which is up to 64,000 on the Arduino. It's only 16 bits. I'm used to 32 bits on most processors, and so that rolled over and was then negative, and so I changed that to long. That was easy. And then on the how long it's run without an error count, that actually wound up being more than 1,000. And so this summary of it, the parenthesis was out here, and I realized I wasn't actually erasing that when I wrote the new value, because I never really expected it to go over 999. And then the big thing was sometimes this value would the error would be 128, and I didn't know what it was. I was very, very mystified. And then I realized that the time was going up 2 seconds at a clip, not every second. So something was not working correctly. And so I worked on debugging that. And here's what happens. That there's a PPS signal that happens every second. And the first thing I do when I notice the PPS is on is I update the date and time and check that I still have a fix. And the way the GPS currently works, or was working, was I would get an update every 2 hertz, so twice a second, and the interface is running at 9600 baud. So if you look at the timing diagram, the PPS comes in, I turn the LED on, and I read and I wait for the first read to come back, and then I flush that. I wait for the second, and when the second comes in there, I know it's valid data. I then do stuff, and I can see that on the oscilloscope with I2C activity. Once that's done, I've updated the display, I've done whatever DAC control word change I need. I exit that loop, and I turn off the LED. And then I wait for the PPS to come back up again. And what I noticed early on was that the LED was on most of the time and is only going off briefly. And I was puzzled by that, but okay, I didn't really give it too much credence. But then, I added a lot more I2C writing and formatting. And what apparently happened was the I2C stuff took long enough that when the time it was done, and then you go look for the PPS again, the PPS already happened. And I have a condition where, if the PPS is up, I don't do the service routine until the PPS goes back down again. So if the I2C was just a little bit longer, I missed seeing it down. And so what would happen was PPS would still be high, and so I thought that it was the same PPS. And when it went low, and waiting for it to go high again, well, I had a 1500 millisecond timeout in case there was no PPS. I'd still update the counters, and so I'd hit that, and I would go through the normal routine, which involved waiting for 2 GPS cycles, and so I'd actually miss this actual PPS, and then I pick it up sometime later. And when I picked it up sometime later, I would have gotten, the count from 2 seconds, which would be off by 180, which is why I was seeing that error. But it took me a long time to figure this out. It was kind of frustrating. And so there are a couple ways of fixing that. At first, well, I'll jump to what I did. I was able to change the serial rate of the GPS interface to 115 kilobaud. So then this time got shrunk. And then I also changed the update rate to 10 hertz. And there's just some software complexity on the order in which you set all these things. And so basically the way it works now is that when PPS goes up, I wait for, I flush it, I get the real stuff, and then I do my I squared C stuff, and then I'm back to waiting for PPS to go up for most of the cycle. So this is a lot of idle, and so I'm only actually busy for about 300 milliseconds. And so the way you can, I sort of noticed this if I look at my system. One of the things that I always found curious was that it was always tricky getting in button pushes. They didn't register as snappy. There was a delay, and then the LED was on most of the time. And now it all makes sense. Since I was always in the service routine, it never really got a chance to look for the buttons. That's why the button pressing was kind of weird. And then the LED was on most of the time, showing I was in the service routine, which makes me feel good about actually including an LED in the system, because I'm usually not one that likes lots of flashing lights. And so the buttons are now, very snappy and responsive, like I hoped. And it's borne out by looking at the oscilloscope and looking at the timing diagram. That I, have lots more idle time. The other thing that I did, then I was thinking, like, this oscillator, wanders around a lot. Can I do better? And so this thing I have right now is an oven-controlled crystal oscillator. It's $150. It's plus or minus 5 ppm, and I can tune it plus or minus 0.7 ppm over basically 1 volts. And real networking synchronization equipment uses rubidium oven oscillators. And I checked, they're $1,900, but they're basically 5 parts per trillion, so they're 1,000 times more stable, and you can tune them over 5 parts per billion over 5 volts. So they're 300 times finer control over the tuning over a range that's 1,000 times smaller. So yeah, $1,900 is pretty pricey. So I'm glad I'm going with the oven oscillator. Because I was wondering why Symmetricom or whose ever equipment has such great holdover. Well, it's this oscillator. So I did some measurements to expand on what I did before. So then I let me change the DAC count by 10 and see what happens. And so I got the error counts. And since there are so few errors, I counted the errors over 10 seconds. And so basically a change of a DAC count of 10 results in 1 less error every 10 seconds, which is consistent with the other data that says 100 counts is 1 error every second. And then I did it with the granularity of 1 count, and there using my notation from the display, at 2078 I was getting 13 seconds between every -1. error. And so I recorded that. And so these are reciprocal frequency offsets. And basically I determined that one DAC count is 1.25 about parts per billion, or it's 124 or 124 actually it's not 124, it's 12.4 millihertz is the tuning accuracy that I can achieve by changing the DAC, but I can measure it to a finer accuracy with the error count. And so I graphed these things, and just like you would expect, it's very, very linear. Here's the by 10 DAC count increment, very, very linear, and the slope of that again is the 1.24 for the coarse DAC control. And then I did the fine DAC control, and this main line here is the first one that I did, but it was taking a long time to do some counts, so I opened up the patio door, which I shouldn't have done, and that cooled things off just ever so slightly, so you can see the data dips down a little bit over here. And then later, I have this outlier here. I think when I was here, when I adjusted it by 1, I actually adjusted it by 2. I was kind of distracted with the music player. But again, nice linear thing. And then a little bit later, I took a second set of data, and that data was offset a little bit. It might have been because the temperature changed a lot, ambient, but then I took some data, and the slope of that line is relatively the same as the slope here, so that depending on the voltage and the temperature at a particular time, this line might shift up or down. Because a lot of times the 2048 default count seems to be pretty good. Sometimes it's it's 2000. Sometimes it's 2060 is a good value, and that's just indicative of this line moving up and down. But it still has the linearity, which means that when I do the actual auto-tuning software, I can use these offsets that I'm finding, or the tuning of the DAC control word. I can use that as initial good guesses, so that again, if I'm measuring 13 errors every 10 seconds, I know that I'm probably off by a count of what in that case would be 100. And so I can dial that in quickly and have it converge. Likewise here, I kind of have an idea. If I'm sitting at plus 10, I probably need to dial it down, or dial it up down by 4 or 5 counts. Then once I'm sort of in this range, you can kick it up once or twice up and down to get to a closer value. So trying to think of what's going to be next. I'm working on a better design, or am I calling a phase comparator? Because right now the PPS comes in, and I have this 10 megahertz signal, but I don't know when this PPS edge is. And the PPS edge jitters around the 15 nanoseconds, but what I wind up doing is when I lose a 10 megahertz edge, I know that, so I can make the clock faster or slower. So I'm always bouncing back and forth, effectively 100 nanoseconds relative to the PPS to try to keep the right frequency. What I'm going to do is I'm going to have a circuit which allows me to measure the PPS edge to the 10 megahertz edge. And that'll give me two things. One of them is as the PPS edge is jittering here, I get the +1 -1, or -1 +1 jitter effect, which clears my error count, which I don't like. And And the other is I have to wait a long time for that edge to drift over for me to detect it. So if I have this phase comparator or phase measuring circuit, the PPS edge, I can see where it is, and then I can adjust my DAC control in a very narrow range rather than waiting it for it to slew an entire 100 nanoseconds. And then I can also make it so that the PPS edge stays away from the sample edge, so I can have it, do its jittering over here and not as it happens, jitter to cross it over. So then that's when I slip the bit backward and forward. So that's what I'm working on now. I had to order some parts, some delay lines, some more registers, and I need to actually work up the design for that. But that's what's coming up next. But again, happy with the results. The clock is can be really stable. The fact that I got 1,000 seconds, or it was 1,108 seconds going by before it slipped an edge, it means it's well into the fractions of a parts per billion, and it's stable. It's 1108 seconds. So that's good news, and hope to be able to show probably in 2 weeks, maybe have the first rev of the phase comparator circuit, so you can actually see where that PPS edge is. Anyway, thanks for watching.